At its simplest, lava is molten silicate rock. But add a little spice, seasoning lava with things like ice, water, crystals, and metal can lead to explosive results. Whoa! Here's how lava reacts to 4 different factors. Ice and lava might feel like an odd couple, but frozen volcanoes are a real hazard in places like Iceland. And it's important to study this interaction for evacuations, especially because lava can move faster and farther on ice. Ash from the volcano can settle on the ice, creating an insulating barrier, slowing the lava's cooling. The ice can also melt, which can reduce friction, and the steam can give the lava this bubbly look. The more the ice melts, the higher the risk of flooding. Jökulhlaups are floods that happen when a glacial lake overfills. In 2010, Iceland's Eyjafjallajökull volcano caused a glacial outburst flood that forced 800 people to evacuate. In the same vein, glacial melt and debris are a perfect recipe for lahars. These volcanic mudflows sweep away homes, infrastructure, and even people without enough preparation. Like the 1985 eruption of Nevado del Ruiz in Colombia, which led to 20,000 fatalities. Lava has some pretty unique reactions to seawater, as you can see in this ocean entry footage shot on the coast of Kalapana, Hawaii. This steamy mist is actually Laze, a cloud of toxic gas. It's made up of hydrochloric acid, the result of steam reacting with lava-heated salt particles. There are also bits of volcanic glass swirling in there. The water cools the lava, which gets crushed up by the waves into volcanic glass and swept up into the plumes. Not something you want to be breathing in. Lava that doesn't shatter will start hardening into a delta, an inherently unstable new landmass. Blobs of pillow lava pile one on top of the other, forming a shaky foundation. When water gets trapped among these hot pillows, it causes a steamy, violent explosion called a molten fuel-coolant interaction. This can sometimes trigger the whole delta to collapse, and to hurl rock and debris over an area as large as multiple football fields. Even when the flow looks slow and unthreatening, you don't know what's happening under the surface. This can apply to the lava itself, too. Crystals form as lava cools. Generally, the quicker the lava cools, the fewer crystals will form and the smaller they'll be. But scientists have found that bigger crystals with more sides slow lava down, giving the lava more surface area to cling to as it flows around. This is important to understand the lava's viscosity. Generally, less viscous flows can move faster and travel farther, knowledge that helps public safety engineers plan hazard maps. So scientists are researching how minerals in unique environments and unique temperatures create different crystals. At Syracuse University, they used metal bits of varying size and shapes to represent olivine, one of the most common minerals in igneous rocks. It has a high crystallization temperature, so it can start forming seeds in the magma even before it leaves the volcano. And the seeds will generally keep growing as the magma flows out of the volcano and slowly starts to cool. But when lava cools instantly, like when it's suddenly exposed to water or air, seeds don't have time to grow. This is why igneous rocks like obsidian are smooth and glassy. And no two volcanoes are exactly the same. Time, temperature, and minerals all matter. That's especially true when it comes to volcanoes on other planetary bodies. In 2022, NASA plans to send a spacecraft to Psyche, an asteroid between Mars and Jupiter that appears to be made of nickel and iron. Researchers believe that if Psyche has volcanoes, they may be metal-based. Features called ferrovolcanoes that spit up metal instead of silica rock, or spurious ferrovolcanoes which combine the two. Ferrovolcanoes are actually still theoretical at this point. We know they're possible, we just don't know what they'd look like. That's why the folks at Syracuse decided to make a spurious volcano using rock and metal. They found that metal moves faster and sinks lower, since it's denser than silicate rock. This means ferrovolcanoes might look a little different. Volcanoes shape themselves as layers of lava build up along the sides. So a pure ferrovolcano would probably look flatter and sprawl farther than the typical conical shape we see here on Earth. By demonstrating how a ferrovolcano would work and look, scientists should be able to recognize and interpret formations found on Psyche. or any other metal bodies that make up the complex geology of our solar system.